In Chapter 5, we're going to begin to talk about continuous distributions. We're going to draw a lot of comparisons and see a lot of differences between how continuous distributions work from the discrete distributions that we talked about in Chapter 4. Now to start here in section 5.1, we're going to focus in on a special kind of continuous distribution known as the uniform distribution. But before we zoom in on those precise details, let's just take a look at this opening motivation and try to get a sense of why we might need a continuous distribution, and how this differs from the discrete distributions we previously discussed. So let's see what we have here in the motivation. Suppose a production line is set up to manufacture plastic modules. Okay, so I don't know, you got some little plastic pieces coming down a conveyor belt, right? This is what the factory is meant to produce. And each module's assembly time varies a little bit, right? So it can vary from, say, 27 seconds to kind of build this whole thing and put it together, maybe up to like 39 seconds, right? But it won't go more than 39, it won't go less than 27. That's where it's kind of locked in. So the question is, what sort of distribution could model the amount of time that it takes for the plastic module to be produced? Notice again here we still have a random variable because the time it takes to produce the module can vary. So we have a variable, and it seems to be produced by maybe just some sort of chance or some sort of likelihood. Some probability might determine how likely it is that it's going to land at any given time within that range. So I can go ahead here and start to kind of set up a random variable. I could say if x represents the amount of time it takes to produce the module, well, then I should definitely be able to tell that this amount of time that, again, it's going to be taking is not something that is ultimately going to be discrete, right? If I'm looking at an amount of time, then time itself is something that needs to be measured, right? Like I'd have to use some sort of like a stopwatch or something like that to measure the amount of time. So if x represents this, then x must be a continuous random variable. Notice again, the reason that we're saying that is because the time ultimately that it takes to produce this module does not just have to be like let's say like a whole second amounts, like 27, 28, 29, 30. It could really be any amount of time from 27 seconds up to 39 seconds. Any time you could think of in between those is a valid option. So the weird part then is how do we think about this? Notice that on our formula sheet, we kind of had different ways to try to organize our thought process. On the first side of the formula sheet, we had this idea that we could go ahead and model discrete distributions. We could organize the way that we thought about them using a nice table, right? We would set up a table and we would do our x's and our probabilities. And this was easy because we could typically like list out the different possible values of x very clearly here. But notice that when I move to the back side of my formula sheet and I start talking about continuous random variables, a table is not going to be a good way to represent this. And part of the reason for that is that if you imagine having a table, what x values would you begin to put in it? Well, if I was to imagine here trying to create a table of x values, I might say 27 seconds is a possible time that it takes to produce the module. But what time would I put next? Because I can't, maybe if I want to list these in order, put down 28, because aren't there times between 27 and 28? Well, there definitely are, right? Like what about 27 and a half seconds, right? Like that's a possibility. But then again, there's still times that could exist in between 27 seconds and 27 and a half. In fact, we could continually, between any two values of x, always place another value of x. And so ultimately, this representation here is not going to be a good one. It's not going to be helpful to try to visualize continuous random variables with a table. So we're going to go ahead and try to make a different visualization a possibility. So here's what I'll state. we may recall that in section 4.1, that's where we talked about discrete distributions, we created probability histograms. And these probability histograms helped us to kind of understand partially like the shape of this probability distribution, helped us understand the behavior. So I'm going to try to go ahead and do the same thing here. So I'll say we will try and construct, or I don't know why I said try and, it's kind of strange wording. How about we'll say we will try to construct a probability histogram for the variable of x. Okay, so we're going to try to create a probability histogram for this. Now this is going to be kind of strange because we're going to have to draw a vertical bar at every single possible value of x imaginable. Now, when we do this, that is, we draw a vertical bar for every single possible time from 27 seconds to 39 seconds, that's technically infinitely many bars. So I'll state this. We will need infinitely many bars to do this. So to help get a sense of what this might look like, let's just suppose, for the sake of argument, that I start sketching out a picture. And I'm going to go ahead and say that this line here maybe represents the horizontal axis I'm going to be building this above. And maybe I start down here at 27 seconds, and I go all the way up here to 39 seconds, okay? Because that's kind of my range of different values for x. And so I'll even label my little number line here with an x on it. Now, if I imagine what my different bars might possibly look like, well, I might have a bar right here at 27, and that might go up to a particular height. And then I might have another bar at another time that goes up to a different height, and another bar that goes up to some other height, and all right, I'm going to have tons of bars. There's no way I could actually kind of plot out all of these, but I could maybe imagine that, like, if I kind of trace all the way up to some of these different points, I can imagine kind of landing at a spot on the graph once I get up there. So these little dash portions are just saying how high I have to go before I hit my point. Now, if I put a whole bunch of these points next to each other all the way across this range of x values, what I'll start to see is that I can kind of imagine connecting all the points at the top, maybe with some sort of a curve. And right now I'm just kind of guessing like what a possible curve could look like here. But what I'll see then is that visually, what I have to maybe help me understand what this distribution looks like is not a table. Oops, let me undo that. But it's not a table, but rather I could think about it as a curve that's going to help me understand what my distribution looks like. So this is kind of an interesting switch. When I had discrete variables, I would use a table. When I have continuous variables, I can imagine creating the probability histogram. That's going to create so many bars that when all jam next to each other, if I connected all their tops, I would get some sort of a curve. So I'll say here that we see that this produces something like a curve. And I can imagine again that each one of these dots came from like an infinitely thin vertical bar that would have been part of that probability histogram. Now, interestingly, if you go back and you take a look at the histograms that we built back in the previous chapter, we'll see that if I was to take, like, say, the heights of all of their bars, or actually what you could count as like the area of each one of the rectangles, and you put them all together, you would have gotten 100%, since all the bars were supposed to kind of add up to a grand total of 100%. So here, I'll go ahead and note that we're ultimately going to end up with the same sort of behavior. So I'll say we note that the area under this curve must add up or total up to be exactly 1, representing 100%. So that is, if I take all of the space kind of between this horizontal line and under this curve, if I add all of that up, I can say here that my total area is 1, which again, remember, is really standing for 100%. So this is going to be a really useful tool for us. We don't have a table with probabilities listed, but we do have a curve, and we are going to have area under that curve equaling 100%. Now, there are many different possible types of continuous distributions, very special ones. And just like in the discrete distributions, how each distribution like the binomial and the Poisson and the geometric, they all had their own type of table. They all filled in different values and got different probabilities. We're going to see the same thing here. We're going to have different distributions like a uniform, a normal, an exponential, a t-distribution, a chi-squared distribution, an f distribution. We'll take a look at all of these actually throughout the rest of this course, many of these throughout Chapter 5. But each one of these is going to have a different sort of a curve that is going to be constructed to help model this particular behavior. So we'll associate a curve, a particular graphical picture, with each one of these individual distributions. Now in this section, we're going to be taking a look at, again, what we call a uniform distribution. And we'll take a look more at what that means in the next video.